Assalamu alaikum everybody. In this lecture number 4 in electromagnetic waves, we're going to talk today about magnetic material, magnetization, and the magnetic circuits. In a descriptive way, the material is composed of atoms. Atoms is composed of electrons and nucleus. The electrons are moving two kinds of motions. First, they are orbiting around the nucleus in some orbits, and second one, it is spinning around itself. Also the nucleus is spinning around itself. So this spinning and rotation of charged particles is sort of like a current loop, and in last lecture we learned that current loop does have magnetic moment associated with it. So this moment of the orbiting electrons equals the current, the equivalent current of this moving charge. Moving charge is a current, and the orbit represents some sort of a loop. So the moment of this loop equals the current I multiplied by the loop area. And because the nucleus is much more weight compared to the electrons, its motion is much smaller and its spinning effect is negligible for like the first order approximation or for the descriptive like analysis we would do. So in the absence of any applied external magnetic field, the orientations of those both orbital and spinning moment are random. Their number is very large, so the net effect is zero. But when we apply external magnetic field, this will cause the spinning electrons to align with the magnetic applied magnetic field. It's giving some sort of like an amplification for the applied magnetic field inside the material. But the orbiting electrons will induce some magnetic field that resists the applied magnetic field. So we have some sort of like an amplification effect from the spinning motion and sort of like a decaying or attenuation effect because of the induced by the orbiting electrons. So if we are to describe this in a mathematical model, that we know that orbiting charge means like some sort of like a current, and this current goes into a loop. So the moment of this current loop equal the current multiplied by the area. When we have a number of those orbits in a certain volume, so the total is the vectorial summation of those moments, all the orbits existing in this volume. So at a certain point, if we want to find the magnetization or the moment at a certain point, we just do this summation over a small volume and take the limit when this volume goes to zero. So the magnetization or the magnetic polarization density or the moment, magnetic moment or magnetic dipole moment at a certain point does have this expression. And if we are to find like the moment inside a certain volume, we just multiply this m with this d volume. So this represents the infinitesimal magnetic dipole moment for the material. And just a revision from last lecture, the moment equals the current multiplied by the loop area for any small loop. We proved this for circular, and we said it's applicable for other kind of loops as well. The direction of this moment is perpendicular to the loop, following the thumb of the right hand side when the fingers rotate with the current. The vector potential A associated with this moment does have this expression that can be expressed this way in terms of the magnetic or dipole moment, and its magnetic flux density B does have this expression. So the infinitesimal vector potential A associated with this dipole moment does have this expression, or it can be also expressed this way. And if we are to find the total vector potential A over any specific volume, we just integrate this quantity. So let us look into this relation here. The curl of M over R, M is a vector, 1 over R is a scalar quantity, can be expressed in this format. And if you look here, this expression and that expression are the same with just different order, so it's corresponding to a negative sign. So this expression here with a negative sign, we can take it outside and we bring this left hand side in. So the vector A can be expressed as the integration of over volume for this expression here, 1 over R curl of M d volume minus curl of M over R d volume. We can also prove that. We didn't see this relation before in vector algebra, but we can prove that the curl of a vector d volume equal minus the integration over the closed surface of F cross ds prime. So we just take this part here. So we just take this part here and substitute this effect here. So we have now the vector A in terms of volumetric integration and surface integration. We know that if the current is volumetric current density, A will be related this way. If it's a surface current density, A will be expressed this way. From second lecture, I think we proved that or showed that. So we have the expression for A in two parts. One part that is the Jm volumetric magnetic moment equivalent, sort of like current, and another magnetic surface current. Jm equal curl of M, Jms equal M cross An. So these are the mathematical model for this manipulation or for the effect of magnetization. In free space we have M equal 0, and we have the curl of B over mu naught equal J, which is Ampere's law. And we know that in free space B over mu naught is H. But when we have M doesn't equal to 0, J will be equal to J plus Jm. So curl of B over mu naught will equal J plus curl of M. You can take the two curls on the same side. So curl of B over mu naught minus M equal J. Remember that M is the magnetization or the magnetic dipole effect, which is proportional to the applied magnetic field. So we can just say M equal some constant multiplied by H. This constant is called magnetic susceptibility, psi or psi M. So now we can say that H equal this side, this is Ampere's law, so B over mu naught minus M equal H, or B over mu naught minus psi M multiplied by H equal H. So we can just say that B equal mu naught multiplied by 1 plus psi. This psi would be called mu r, which is relative permeability, and the relationship between the B and H inside the material equal the mu, which is permeability of the material multiplied by H. So this relation here is in isotropic material, the material that the direction of H and B are always in the same direction, but there is some other kind of material, it's called anisotropic material, and it does have different directions between B and H. The relationship between B and H in that way is not just like a constant, it is a tensor, which is like a 3 by 3 matrix. If B is applied in X, it can produce H in the 3 different directions based on those parameters, and this material is called anisotropic material. Just for your information, we are not gonna deal with this in our course, but just to let you know about it. So now we need to talk about the magnetic material classification. It's similar to what we do in electricity. We say that we have like two main categories of materials, conducting material and insulating material. Later on, we introduce another material, which is the semiconductor. So we can say from electric properties perspective, we have three categories: conductors, insulators, and semiconductors. Something similar here in magnetic material. The classification is based on their response to applied external magnetic field. And that is mainly because of their atomic magnetic moment. As I just said earlier, on the atomic molecular scale, electron orbital configuration does have its own moment, spinning does have its own moment, and nuclear spin does have also its moment. But in our analysis or in our classification, we're going to neglect this nuclear spin because their amount is much smaller compared to the others because of its slow motion, because it's like heavy component, heavy in weight, so it's moving much slower. Also, for some materials, electrons occurs in pairs, so they will have equal and opposite spin momenta. For non-permanent magnetic material, in the absence of external applied magnetic field, the magnetic moment will equal 0. And as we said earlier, that's because the random orientation of their atomic dipole, either the spinning or the orbital. When we apply external magnetic field, two effects occurs. So the spinning electrons will try to orient themselves along the applied field, causing some amplification for the applied field, and the orbital motion will try to induce a magnetic moment that resists the applied one, which is negative, and according to a law called Lenz's law, the induced magnetic moment always opposes the magnetic field causing it. So we'll be describing the material behavior qualitatively in this course, because the quantitative and mathematical description of the material requires quantum mechanics. So the first category that we're going to talk about is diamagnetism, diamagnetic material. So this diamagnetic material will induce a magnetic moment negative when we apply external magnetic field. Why? Because the orbital effect is dominating the material, and all of this is caused by the internal structure. So this effect exists in any material, the orbital will try to resist the applied magnetic field, and the spinning will try to align with the applied magnetic field. But here in diamagnetic material, the diamagnetism is the dominant, but this, again, like this effect or this resistance is like very small and negative. The susceptibility, magnetic susceptibility, is negative and small. So the mu r, the relative permeability, is less than 1. This effect is non-permanent. It disappears with the absence of applied magnetic field. Material like copper, gold are of this category. The second category is paramagnetism, paramagnetic material. This paramagnetic material, like the dominant effect, is the spin alignment effect. It exists in all material, but it's dominant here. So the susceptibility is positive, but very small, and mu r is slightly larger than 1. This also, paramagnetism is temperature dependent. It's stronger at lower temperature, because when you increase the temperature, the vibration of the electrons increase and its randomness will increase, which will decrease the effect of spin alignment. This is non-permanent effect. It will disappear after removing the applied field. Material like potassium and tungsten are of this kind. Ferromagnetic material, ferromagnetism, this is what we call in the regular life as magnetic material. So this material internal structure is like this. So instead of having each atoms oriented in a its own way, there is some sort of domains, and inside each domains the moment of the different atoms is aligned in sort of very close aligned to one another. So instead of just having a randomization based on atoms, we have randomization based on a collection or groups of atoms. Each group of those is called domain, and there is a separation between adjacent domains by what is called domain walls. Those are still random, like the orientation of those domains are still random, and the total effect or the total moment of this material in the absence of applied magnetic field from external is still 0. But their behavior to applied external magnetic field is different than the other material. When you apply external magnetic fields, what happens is that the domains that are close in orientation to the applied magnetic field will grow, and the others that are in a different dimensions or different directions far from the applied magnetic field will shrink. And their effect, it goes like this. When the external applied magnetic field, so this is H and this is the applied magnetic field B, when we apply little magnetic field, the orientation will happen of those domains, and when we remove it, it will go. So it's linear and non-permanent. But when we go with a stronger applied magnetic field, we will have some sort of a magnetization curve that is called it's called the hysteresis magnetic curve. So when the magnetic field applied from outside start to be larger, the effect, the magnetization effect, start to be irreversible. It start to be nonlinear, and will have some hysteresis, and hysteresis here is some sort of permanent effect. So for example, if we apply the strong magnetic field B2, H will come to here, but when we just remove it, when we apply H, B will go here. When we remove H, come to here, there will be some permanent effect, permanent magnetization effect inside the material. This is called residual or hysteresis. And when we go with a stronger applied magnetic field, at certain point the material will reach saturation, so we can't get higher B than this value. When we remove the applied magnetic field completely after saturation, the material will return back to what's called residual flux density. So this is the maximum residual magnetic field that can remain in the material after the removal of the external field. In order to remove the magnetization, we need to do one of two things. Either we apply an inverse magnetic field, so if we start to apply the magnetic field on the other direction, the magnetic flux density inside the material will start to shrink and reduce till it is vanished, and this value of the reverse magnetic field is called coercive field intensity. So this is the field in the opposite direction that is needed to remove the maximum permanent or residual flux density. Also, by heating up the material to high temperature like 770 degrees, the material will lose its magnetization. Why? Because heating will cause a lot strong random motion, and the arrangement of atoms in domains and the alignment of those domains with the externally applied magnetic field will start to be random, and once you remove the heat, everything will return back to the random shape with zero permanent magnetic flux density inside the material. So this hysteresis or this residual represents some sort of power loss, and we can, based on this, the ferromagnetic material can be classified as either soft or hard. So soft and hard depends on the level of the permanent BR, the residual permanent magnetic flux value. If this value is small, like this case, we say this is a soft ferromagnetic material and its hysteresis curve will be slim and thin. If the residual permanent magnetic field is large, we are saying this is a hard ferromagnetic material. So this one is very good for transformers and AC applications in general. Why? Because, as we said, hysteresis is some sort of a power loss, and here the power loss is much smaller. This is good and desirable for permanent magnet because we can have large amount of magnetism stored, and it's a loss, but it is sort of still in the permanent magnet. Some other material are antiferromagnetic material. This material does have adjacent magnetic moments are oriented in opposite direction. So when we apply external magnetic field, it will produce no change on the flux density, like nickel oxides and some other material. It's temperature dependent, and after certain temperature the coupling between atoms will be lost and the material will start to be paramagnetic. So if we heat it up to high temperature, the coupling that makes adjacent moments oriented in opposite direction will be broken and the material start to behave like a paramagnetic material. Another category is ferrimagnetic material. It's very similar, so it's some sort of between ferromagnetic and anti-ferromagnetic. It does have opposite oriented dipoles, but one of them is stronger than the other, so there will be an effect. This effect is not as strong as ferromagnetic, and it's not as low as anti-ferromagnetic. It's somewhere in between. So it's a subgroup of ferromagnetic material. It does have low conductivity, and its application is in high frequency and RF applications. So this is paramagnetic material. This is ferromagnetic material, the strongest. This is ferrimagnetic material, which does have some opposite ones. Anti-ferromagnetic material that does have equal and opposite, so it's not affected by externally applied magnetic field. I recommend that you watch those two videos to visualize some of the experiments that show like what we talked about in this lecture. In this part of the lecture, we're going to talk about magnetic circuit, which is something in analogy to electric circuits. In electric circuits, we are concerned with finding voltage and current in different parts of the circuit. In magnetic circuits, we will be concerned with finding the magnetic flux B or phi in different parts of the circuit. Magnetic circuits, as we're going to see, is something related to generators, motors, and transformers. And we have two basic equations. Number one, divergence of B equals 0. And number two, the curl of H equals J. So the first one is the law of continuity or conservation of magnetic flux, and second one is Ampere's law. So let us look into the analogy between electric circuits and magnetic circuits. So in electric circuits, we have J equals sigma E. In magnetic, we have V equal mu H. Total current I equal the integration over any open surface of J dot ds. Flux phi equal the integration of B over open surface S. So easily you can see analogy between I and phi, B and J, mu and sigma, H and E. So there is good analogy, and when we have analogy, we can use this in like solving problems. So we can model magnetic circuits, as we're going to see, into electric circuits, and then apply all the electric circuits law that we are familiar with. In electric circuits, we have Kirchhoff's law, we have Ohm's law, we have like V equal I multiplied by R. In magnetic circuits, we will have something similar to Ohm's law, where we have F magnetic, which is magnetomotive force, equal phi, which is analogous to current, multiplied by R, which is analogous to resistance. This R is called magnetic reluctance. We have R equal length divided by sigma S, the reluctance equal L divided by mu S. So the mu, the permeability, is something similar to the conductivity of the conductor. So the magnetic motive force, magnetomotive force, is the integration over closed path of the current of H dot dl. And this is easily can be equalized to N multiplied by I when we have wound coils. So if we have a coil, the magnetomotive force of this coil equals the number of turns multiplied by the current I. So let us apply like this analogy of magnetic circuits and electric circuits into this problem that we solved before for the toroid. So for this toroid, we have N turns. So we have magnetomotive force, and we have a path that would have a flux. The flux here is confined to a path. So this core here is acting as electric wire, like conducting wire, that carries the magnetic something analogy to current, which is the flux. So the reluctance of this path equal length divided by mu s. Length divided by mu s. The S is the cross section, which is B minus A multiplied by H, and we will have the length of this path equal to by rho m. Rho m is the medium or the average path radius, which is this blue distance. So phi multiplied, phi is analogous to current, reluctance is analogous to resistance, magnetomotive force is analogous to voltage, so voltage over current equal flux equal current. So magnetomotive force is F, M is Ni, R equal this denominator, it goes up, and at the bottom we have 2 by rho m. So we can say H, which equal B over mu. What is the relationship between B and phi? B equal phi over S. B equal phi over S. So from this relation we can find H, and we will find that H equal Ni divided by rho m. So this is exactly the same results that we got before. So here this magnetic circuit is modeled electrically as this circuit here, where we have voltage source, its value equal Ni, and reluctance. So solving the problem this way is coming like very easy. So here we're just saying that it is the same results that we found using Ampere's law. So for this problem, we can solve it with magnetic circuits. We can solve it with Ampere's law. So in the previous solution, we assumed that this cross section is very small, so the field is uniform along this one. But if this assumption is not valid, so here we assume that B minus A is much smaller than A. So like this width here is very thin compared to the radius of the outer part of the core. If this is not valid, we need to like calculate more accurate results. So here the relationship between B and phi would have like more like different expressions. Phi would equal B dot ds. We know that B equal mu Ni divided by 4 by R. So we integrate over the cross section, so we'll come up with a different expression if we take no approximation about the cross section here. But if we assume that B minus A is much smaller than B, so this, if we assume this thickness of the core is much smaller than the outer radius, much smaller means less than 0.1 of it. If we assume that, we'll have the easier solutions that we had before. And in all cases, Ni will equal phi multiplied by reluctance. So even the calculation of the reluctance will be different than the previous case. Here we have another problem, which is a toroid with air gap. So if we have an air gap into the core, we can solve this problem using magnetic circuit approach. So the modeling here will be different because the phi will have two different media, the core and the air. So actually in this circuit we have two resistance or two reluctances, the core reluctance, the gap reluctance. So the reluctance equals the length here, 2 by rho minus gap thickness, T, divided by mu S. The gap is, length is T, divided by mu naught, because it's air, multiplied by S. Here we assume the gap is too short or like too small, so that we don't have fringe effect, and from this assumption T is small enough so that the flux that goes out of this part and goes into this part didn't change its shape, so the cross section of the flux in air is the same as the cross section of the flux in the core. So here the reluctance will have this expression, and if we choose the core to be ferromagnetic material with like 10 to the power 5, 10 to the power 4 relative permeability, we can easily neglect one with respect to mu r and would have this expression. So this is r, and we have the same magnetomotive force, so we can calculate the flux, and as I said, we choose the gap to be small enough so that the flux doesn't change its cross section from one part, which is the core, to the other part, which is the air. So this is the approximation after neglecting one, and because the cross section is the same, the flux is the magnetic flux density B is continuous. The magnetic flux density in core, in gap, they are the same, and they are equal in the I, which is magnetomotive force, divided by R total multiplied by the cross section. So we have this value here. H core is B divided by mu R mu naught. It will have this expression. H gap will have B divided by mu R mu naught, which have this expression, which is mu R HC. So as I said, HR can be 10 to the power 4, 10 to the power 5. So H gap is much larger than H core with this factor, and we can like generate a very high magnetic field intensity using this approach. When we are dealing with ferromagnetic material, solving this problem is not easy. Why? Because we don't know what is the operating point. So if we know B, we don't know H, because we don't know at what part of the curve is and what is the history. So if we have like H, we will not be able to know about B except we know the hysteresis curve and the history of this magnetic material, so that we can find the operating point and relate H to B. So this is something about solving a problem in ferromagnetic material, is like the history and nonlinearity is something important. So if we are dealing with a ferromagnetic material, and this is the expression, finding B in terms of magnetomotive force, B is unknown. Also, mu R is unknown. Why? Because we don't know which part of the curve it is and what is the hysteresis curve. So this is what need to be like solved, but in our course we will not handle those kind of problems in. So we'll assume mu R is fixed or known value. Another example here is this sort of like transformer. We have coil 1, we have coil 2, and we need to find the magnetic field in the central arm. We need to find the magnetic field here. So we have magnetomotive force 1, we have magnetomotive force 2, and you must pay attention to the direction of this magnetomotive force. So this is acting as a battery. So is it like the positive is that way or the positive is the other way? In order to know, we use the right hand rule. We put our fingers along the coil rotation. Our thumb will point to the direction of the current. So the positive from this one is going this way. And on the other one, again, we put our fingers, right hand fingers, along the direction of rotation of the coil, and also like the positive is in that way. So this coil here is pushing flux that way, and this coil is pushing flux that way. So we have two loops here. We can apply Kirchhoff voltage loop on this one. We apply Kirchhoff voltage law on this one, and remember that the two flux, which represent or analog to currents, is like both of them are flowing in the middle arm. So we can write the two equations for loop 1 and loop 2 here. For loop 1 we have, so this is the electrical model, reluctance here, reluctance here, reluctance here. The reluctance here depends on the length, this length, 1, 2, 3 arms, the sum of them. R3 is the length of this arm, and so like this arm length equal to L1 plus L3. This arm length is L3, this arm length is 2L2 plus L3, or like here I think the notation that we have is this is L1 and this whole length is L2 and this length is L3. So on the loop number 1 the voltage is in that way. So like this voltage will equal reluctance 1 phi 1, which is the reluctance 1 is this area here, or like this length, sorry, plus the current flowing here. We assume this is the positive, so this is pushing phi 1 and this is pushing phi 2, so they are summed to one another. We do the same thing for loop number 2. Then we have this expression here, and we can continue from this point. We can continue solving this problem as any like circuit problem issue. So phi 3 is the one that we are interested in, which equal phi 1 plus phi 2. So we can just like rearrange the equations to find this expression, and this will equal phi 3. We know N1 I1, N2 I2, the three reluctances are known, and the problem is solved. And this is the learning objectives for this lecture. Thanks everybody for watching the video, and meet you in the discussion session inshallah. Assalamu alaikum.